video is on molar enthalpies and thermochemical equations and how we represent these energy changes in chemical reactions. So the first thing we're going to look at is a molar enthalpy, which is basically the enthalpy of a mole of a substance. So when we look at the title here of my slide, you can see the symbol for molar enthalpy. I've got a delta symbol, which means a change in energy. I've got the H to represent enthalpy, and the little X is basically symbolizing the different types of enthalpy that we can look at, the different types of chemical reactions that we can measure the enthalpy of. So we'll talk about the little X in a few minutes. So for right now, if we look at any thermochemical equation, represents the energy change that accompanies a chemical reaction. So here's an example of hydrogen and oxygen combusting and making a water molecule. And when it does that, it releases 483.6 kilojoules of energy. So the equation that represents the energy released when we only burn 1 mole of hydrogen instead of 2 would be that exact same reaction, but everything's cut in half. So my coefficients have all been cut in half, and my energy has also been cut in half because obviously I'm only burning half the amount of hydrogen. So the enthalpy change per mole of a substance then is called the molar enthalpy, delta Hx, where X represents the type of change that is occurring. So if you look at table 1 on page 306, there's a bunch of different enthalpies there. You have enthalpy of combustion, enthalpy of vaporization, so it depends what the chemical reaction actually entails. But we'll look at that in a little bit more detail later on. So the molar enthalpy for the combustion of hydrogen is labeled with a delta H to symbolize enthalpy. COMB is, I write instead of that X because now I'm dealing with a specific reaction called a combustion reaction. And because it's exothermic, it is negative, and when I've divided it by 2, I get 241.8 kilojoules per mole. So a little more molar enthalpy. Enthalpy changes for exothermic reactions are always given a negative sign. Enthalpy changes for endothermic reactions are always given a positive sign. Heat is a reactant. The molar enthalpy of a physical change may be expressed similarly. So if I go from water as a liquid to water as a gas, I obviously have to add in energy to it in order to change it from a liquid to a gas. So if I want to change 1 mole of water from a liquid to a gas, it'll take about 40.8 kilojoules of energy. So thus the molar enthalpy for vaporization is delta H vap. And again, I put the VAP down to symbolize that I'm talking about a vaporization reaction. Notice that in this case it's positive because I had to input energy in order to make this reaction happen. So this is actually an endothermic reaction. All right, a couple more points on this. The amount of energy involved in a change depends on the quantity of matter that's undergoing that change. So to calculate the enthalpy change, delta H, for some amount other than a mole, we use this formula. Delta H is N of delta Hx, okay? So that basically looks at, if you look at the units, we end up canceling out moles by multiplying your delta Hx by the number of moles. So we're going to go through an example of this. So N is the number of moles, and delta Hx is the molar enthalpy, which is kilojoules per mole. So if I just want to find the amount of energy, not necessarily the energy per mole, I'm going to use this equation. So let's go through an example. A common refrigerant, Freon 12, and I gave you the molar mass, 120.91 grams per mole, is alternately vaporized in tubes inside a refrigerator, absorbing heat, and then condensed in tubes outside the refrigerator, which releases heat. This results in heat being transferred from the inside to the outside of the refrigerator, and that's why your fridge can stay cold. The molar enthalpy of vaporization of Freon 12 is 34.99 kilojoules per mole. So for every 1 mole of Freon 12 that gets vaporized, it basically requires that much energy. If 500 grams of Freon 12 is vaporized, what is the expected enthalpy change? So how much energy would that require? So first off, we have to deal with moles here. So the first thing we're going to do is actually convert from grams to moles. So my moles of Freon 12, I'm looking at converting 500 grams of my Freon-12 to moles. So in order to do that, I need to divide by the molar mass, or multiply by 1 mole over the molar mass. 120.91 grams. So in this case, my grams will cancel out. I do 500 divided by 120.91, and I get 4.135 moles. So I know how much energy is needed to change 1 mole of Freon-12 from a liquid to a gas. But I don't have 1 mole in this case. I have 4.135 moles. So what is my enthalpy change? Delta H. That's what I'm trying to find. I'm going to use my N delta H. And instead of X, I should actually write that it's a vaporization reaction. So when I do that, I get 4.135 moles. And I multiply that by the molar enthalpy, which is 34.99 kilojoules per mole. 34.99 kilojoules per mole. And if you look ever so nicely, your moles end up canceling out. And your final answer is 144.7 kilojoules. So that's how much energy is needed to transfer 500 grams of Freon-12 from a liquid to a gas. And of course, my smartboard is not cooperating with me today. Here we go. Oh, nope. All right. All right, so calorimetry of physical changes. So what we're going to do in the lab is we're actually going to use a calorimeter to get these values for molar enthalpies, and we're going to use a calorimeter to calculate a change in temperature, which will eventually translate to a change in energy. So how do we get these values for molar enthalpies? Well, first off, to study any energy change, we have to have an isolated system. So what we're going to use for that is what's called a calorimeter, and we're going to use very precise measurements. So when we do calorimetry and when we do these lab experiments, we're actually making 3 assumptions. We're making the first assumption that no heat is transferred between the calorimeter and the outside air or the outside environment. Any heat absorbed or released by the calorimeter materials, such as a container, is very negligible and really small, so we don't consider it. And a dilute aqueous solution is assumed to have a density and a specific heat capacity equal to that of pure water. So anytime we deal with solutions in our calorimeter, basically all of our solutions are going to be very dilute so that we can use the specific heat capacity of water in our calculations. So here is kind of how calorimetry works. So this whole analysis is based on the law of conservation of energy, which means the total energy change in your chemical system or your chemical reaction is going to equal the total energy change that happens in the surroundings. And that's what we can measure with a thermometer. So if you look at how a calorimeter is set up, you can sort of see that it's insulated, and inside this little vessel here, this is where the chemical reaction is actually happening, and that's where the thermometer is inserted, so we can see the temperature change. So what actually ends up happening is when your reaction happens, it'll change the temperature of the water that it's occurring in. We can measure that change in the water, and we can use that to determine how much energy is being absorbed or released. Oh, and again, my smartboard is not cooperating with me. So, in calorimetry, if the reaction is exothermic, the energy is given off or released, and it will cause the temperature of the water, which is your surroundings in the calorimeter, to rise. If the reaction is endothermic, energy will be required for the reaction to occur, which means it's going to be absorbed. This energy will be removed from the water, causing the water temperature to drop. By noting the temperature change of the water in our calorimeter, we'll be able to calculate how much energy was actually exchanged in the reaction. So we have to remember that whenever we're doing these experiments, when we calculate the temperature, we're actually calculating the temperature change of the water. That will dictate whether or not the reaction is endo or exothermic, okay? But it always ends up being the opposite. So let's go through another sample problem so I can show you how this works. in a calorimetry experiment, you have 5.56 grams of sodium chloride dissolved in 75 mils of water, has an initial temperature of 24.9 degrees. The final temperature of the solution actually dropped to 23.7 degrees. What is the molar enthalpy of solution of sodium chloride? So in this case, the first thing we've got to do is find the amount of heat that we transferred. So find amount of heat transferred. So in order to do that, we're going to use our Q equals mc delta T formula that we used before. In this case, our mass is going to be our mass of water. So the amount of heat, so when you dissolved this sodium chloride, all the energy got transferred to or from the water. So whenever we do the heat transferred, we have to look at the water, because that's what we're measuring. We're measuring the temperature of the water, and that's your surroundings, okay? So I'm not actually measuring the temperature of the sodium chloride. So my mass of water in this case was 75 mils, which is the same as 75 grams. Your specific heat capacity of water is 4.18 joules per gram degree Celsius. And your change in temperature in this case went from 24.9 down to 23.7. So if I subtract 23.7 minus 24.9, I actually get a negative number, which is fine. When I punch in all those numbers, I get negative 376.2 joules of energy. So that amount of energy came out of the water and went into the sodium chloride so that it could dissolve. So that's step one. Step two, we're going to find the number of moles of NaCl. So the moles of NaCl that was actually put into the calorimeter. So in this case, I had 5.56 grams. So I divide that by my molar mass to get the moles of sodium that was dissolved in this water. It ends up being 0.0951 moles. So in this case, what you have to remember to calculate the molar enthalpy, so that's the amount of energy that's required or released for 1 mole of sodium chloride that's dissolved, you have to remember that the heat lost by water basically equals the heat that is absorbed, in this case by the system, or by the NaCl dissolving. So in this case, they end up being the opposite sign. Okay, so your delta H of solution to dissolve this water ends up being negative Q over the moles, which is negative 376.2. Oh, sorry, negative 376.2 divided by 0.0951, and that's 3.96 times 10 to the 3 joules per mole of sodium chloride that dissolves in water. Okay, we have one more example to go through. So I think my smartboard is going to act up on me. So what I think we'll do is we'll stop the video there. We'll do the last example in class and hopefully clear up any misconceptions that you have after that.